Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to conclude the topic we discussed partly in the previous lecture. So we will continue with that. Our topic in the last lecture was the DEBYE model. Model of what? Of heat capacity of a solid. So today we will continue this topic and hopefully we will conclude it. So I write continued. So let us continue. In the last lecture, we obtained this equation. I'll write it CV is equal to 3V by 2 pi square Vs cube h cross square over kt square. Then let me change the color for the integral 0 to theta d over t x raised power 4. Oh, sorry, I made a mistake. Let me correct it. This was 0 to omega d. Then we had omega raised power 4 e raised power h cross omega by kt. Then in the denominator we have e raised power h cross omega by kt minus 1 square d omega. I will check the equation first before going forward. CV is 3V over 2 pi square Vs cube h cross square by kt square. Then we have integral 0 to omega d omega raised power 4 e raised power h cross omega over kt. Then in the denominator we have e raised power h cross omega by kt minus 1 square d omega. I will name it equation first. Under this lecture, I will name it equation first. And you know the symbols. V is volume of the sample. Vs is velocity of sound through the solid material. K is Boltzmann constant. H bar is h over 2 pi, where h is Planck's constant. T is absolute temperature. Omega is angular frequency. And omega d is what we call DEBYE frequency. We have defined DEBYE frequency in the last lecture. Now this equation gives us what? It gives us the expression for molar heat capacity at constant volume for a solid material according to Peter DEBYE's model, right? Now we can simplify the appearance of this equation by changing to a dimensionless variable. So what we do, we take another variable x equal H cross omega by kT, and we define d by temperature, theta d as k theta d equal to H cross omega d. So I'm saying we can simplify the appearance of this equation 1 by changing to a dimensionless variable x equal H cross omega by kT, and we define a quantity d by temperature theta d as k theta d equal to H cross omega d. When we do this, equation 1 becomes, I will write it in another page, it becomes Cv is equal to 9R times T over theta d whole cube integral 0 to theta d over t x raised power 4 e raised power x over e raised power x minus 1 square dx. I will name it equation 2. Let me check it. Cv is equal to 9R t over theta d whole cube. Then I have integral 0 to theta d over t x raised power, this is x4 e raised power x over e raised power x minus 1 whole square dx, right? Now we need to understand where the velocity of sound Vs has been eliminated by using the equation omega d is equal to Vs times 6 pi square n raised power 1 over 3. Let me check it, where the velocity of sound Vs has been eliminated by using omega d is equal to Vs times 6 pi square n raised by 1 over 3, and you know n is the concentration of atoms in the solid, which is Avogadro's constant Na over V, volume of the sample. Let me encircle these equations. This is now my main equation for Cv. It looks simple. Now I give you homework here. So this is your, I tell you, check it. This is your homework. So what you have to do, you have to check that when we make change in the variable, when we define x equal to h cross omega by kt and define d by temperature by this equation, and use this particular equation for DEBYE frequency to eliminate Vs, your homework is to check that equation 1 becomes equation 2. Got it? I'm saying when I change the variable to x and define my DEBYE temperature and make use of this equation for DEBYE frequency, eliminate Vs, equation 1 becomes equation 2. You have to check it at home. This is your one home assignment. So let us move to now equation 2. So this equation 2 is now the specific heat in the DEBYE model. This is same as equation 1, but we have made it simpler. So this equation gives us now the specific heat. I should write, don't get confused, I will write heat capacity. CV is actually molar heat capacity at constant volume. So it gives us heat capacity in the DEBYE model. Now to compare this equation 2 with experimental results, one must know the DEBYE temperature theta D. Now how we determine theta D? This is determined by choosing the value which when substituted into equation 2 yields the best fit over the whole temperature range. Now we see from equation 2 that if CV is plotted versus a reduced temperature, what is reduced temperature? T over theta D is called reduced temperature. So if we plot CV from equation 2 versus reduced temperature T over theta D, then the same curve, we obtain same curve for all substances. That is, there is a universal curve for heat capacity, right? Now, the value of theta D, that is DEBYE temperature, depends on the given substance, right? And a typical value for theta D, a typical value of theta D, that is DEBYE temperature, is about 300 degree Kelvin, right? Now if we solve for DEBYE frequency, the corresponding DEBYE frequency, we know DEBYE frequency is K theta D by H bar. When we calculate it, it is about 3 into 10 raised power 13 per second. I'm saying the value of theta T depends on the given substance, but when we see different values of theta D for different elements and compounds, we see that a typical value of DEBYE temperature theta D is 300 Kelvin, and the corresponding DEBYE frequency when we solve using the defining equation omega d equal to k theta d or h bar, it is about 3 into 10 raised to power 13 per second, right? Which lies in infrared region of the spectrum, which lies in the infrared region of the spectrum, right? Now, this frequency may also be evaluated from this equation. Omega d is equal to Vs times 6 pi square n over 1 over 3, which we have discussed in the last lecture. So we can solve for omega d from this equation. Omega d equal to Vs times 6 pi square n raised to 1 over 3. Also, I've already written this equation here. I'm rewriting it. So when we do this, substitute the values for Vs equal to 5 into 10 raised power 5 centimeter per second, and n, concentration of atoms in the solid, as 10 raised power 22 atoms per cubic centimeter. Put it in this equation. Vs 5 into 10 raised power 5 centimeter per second. Small n equal 10 raised power 22 atoms per cubic centimeter. What we get omega d approximately 4 into 10 raised power 13 per second. 4 into 10 raised power 13 per second, which is of the same order as we calculated here above, this way, from omega d equal to k theta d over h cross, and putting for theta d 300 degree Kelvin. Now we note here that what we need to note, we note that theta d can be approximated to omega d, which itself can be approximated to Vs n raised power 1 by 3. You can see theta d can be written approximately equal to omega d if we throw these constants, and omega d itself can be approximated with Vs n raised by 1 over 3 from this equation. If we drop this 6 pi square over 1 over 3 constants, so what information we can obtain from this, and consequently what we can do then, and consequently we can say theta d is approximately square root of y over rho times n raised by 1 over 3. How? Because this is velocity of sound, which can be written as square root of y by rho. Rho is density, y is Young's modulus of the material. Then I can write it another approximation, y by m. First I write it square root of y by rho times n raised by 1 by 3, then square root of y by m, where y is Young's modulus and m is the molar mass or the atomic mass. You should write here molar mass. So y is Young's modulus, m is the atomic mass or molar mass, m is the atomic mass or molar mass, and we have used here rho equal to nm and made the approximation. We use this rho equal to nm. So what information is obtained from this approximation? We see the DEBYE temperature theta d depends primarily on elastic constant of the substance y and on the atomic mass m. The stiffer the crystal and smaller the m, the higher is theta d. This explains, for instance, why theta d is high for carbon. For carbon, theta d is 1860 degrees Kelvin, which is stiff and light, and low for lead. For lead, theta d is 102 degrees Kelvin, which is soft and heavy. That's why theta d is low. So we obtain this information from this approximation. Let us now move back to our this equation 2 for heat capacity in the DEBYE model. Now we can demonstrate that equation 2 gives us the correct values in the approximate temperature limits. Let me write it. Equation 2 gives us the correct values in the approximate temperature limits. Temperature limits, right? This is a general equation, equation 2. So let us see that. Now at high temperatures, at high temperatures, T is much greater than theta d. So the upper limit of the integral is very small. I am saying at high temperature t is much greater than theta d, so the upper limit of the integral is very small. Which integral? The integral in equation 2, that is this equation, because upper limit is theta d over t. When t is larger than theta t, this limit becomes very small. Then in that limit, this integral, let me write it. What is my integral? 0 to 0 to theta d over t. Then what is inside the integral? X raised power 4 e raised power x over e raised power x minus 1 square dx. Check it. 0 to theta d over t, x raised power 4 e raised power x over e raised power x minus 1 square dx. That is this integral in equation 2. I will check it. X raised power 4 e raised by x or e raised by x minus 1 square dx. Right. Now under this limit, this integral, when we evaluate, this integral becomes 1 over 3 theta d over t whole cube. 1 over 3 theta d over t cube. This is your home assignment 2. Check it at home. What you have to do, you have to see when t is much greater than theta d, this integral is equal to 1 over 3 theta d over t whole cube. You have to make a calculation at home. This is your home assignment 2. Remember the home assignment first, which we have already discussed, that you have to see that equation 1 reduces to equation 2 when we make the variable change, right? Now, therefore, at high temperatures, equation 2 becomes, what will it become? This is my equation 2. So in front of it, I have 9R times t by theta d or cube, 9R times t by theta d cube. Now what I do, I multiply with the value of the integral obtained, 1 over 3 times theta d over t cube. This is my integral value, 1 over 3 theta d over t cube. So I have made the multiplication, 1 over 3 theta d over t whole cube. What happens? This will go, t cube will go with t cube, theta d cube will go with theta d cube. What do you get? We get 9 over 3, which is 3. So you get 3R. Let me name it. This is my equation 3. You can see this is simply, as you know, the Dulong fitted law. So you can see at high temperatures, the DEBYE equation reduces the Dulong-Pettit law CV equal to 3R, right? And this theta D is typically close to room temperature. So we see that CV begins to approach its classical value 3R for T equal to room temperature and above. Now let us move to the low temperature limit, which is more interesting. Now at low temperatures, T is much less than theta D, and the upper limit of the integral, which integral? Integral in equation 2, our main equation, this one. So the limit of the integral approaches infinity. Now this integral in this limit, let me write this integral again. What is my integral? 0 to theta d over t x4 e raised power x over e raised power x minus 1 square dx. Now at low temperatures, when t is much less than theta d, we said the upper limit of the integral approaches infinity, and this integral which I have written again, 0 to theta d over t x4 e raised by x over e raised by x minus 1 square dx. This integral becomes, or when we calculate it, gives us the value 4 pi raised by 4 over 15. 4 by 15 pi raised power 4. We need to check it at home. Check it at home. You have to see in this temperature limit, low temperature limit, this integral is equal to 4 pi raised by 4 over 15. You have to make a calculation, use a bit of paper and pen and mind. So you will get your answer. This is your home assignment, third. When we substitute this value in equation 2, so at low temperatures, equation 2 becomes, we have CV equal to 9R times T over theta D cube. Then I substitute the value of the integral, which is 4 by 15 pi raised by 4. Let me check it. 4 by 15 pi raised by 4. So I have written it. And in front of the integral in equation 2, I have 9R t by theta d cube. 9R t by theta d cube. So let us make the calculation. What will we get? When you make the calculation, you will get CV equal to 12 pi raised power 4 over 5 R times T by theta D whole cube. Let me name it. This is my equation 4. 9, 2 this, 3 3s are 9, 3 5s are 15, then you have 3 times 4 is 12, then you have in the denominator 5, so you get 12 by 5, then you have pi raised by 4, then you have r times t by theta d whole cube. 12 by 5 pi raised by 4 r t by theta d cube. This shows the t cube dependence, which we have already discussed. You can see at low temperatures, Cv is proportional to Tq, right? Now let us, if you remember in Einstein model, at high temperatures that was okay, that was also giving us the Dulong-Pettit law, but at low temperatures that had a problem that gave us the exponential dependence on temperature, which doesn't match with the experimental results. At low temperatures, experimentally heat capacity varies as T cube. So that result is now predicted by DEBYE model of heat capacity. Now the reason for the error in the Einstein model at low temperatures is now evident. Einstein model ignores the presence of very low frequency or long wavelength modes which can absorb heat even at very low temperature because their energies of quantization are very small. The exponential freezing of the modes does not actually occur, and the heat capacity has a finite value, small though it may be, right? Now, DEBYE model predicts T cube dependence at low temperatures, so that is it is success. But DEBYE model also remains only an approximation. Now, why so? We have already discussed that the nature of approximation, as we pointed out in the previous lectures, lies in assuming the continuum dispersion relation to hold true for all possible modes of excitation. I repeat, DEBYE model has success in predicting the T cube dependence of heat capacity at low temperatures, but this is also an approximation, and that approximation lies in assuming the continuum dispersion relation, which we have already discussed, to hold true for all possible modes of excitation. So this is all for today. Let me summarize my lecture before leaving. We started with the equation which we obtained in last lecture. Then we simplified it by making a variable change, and we gave I gave you this homework to check it. That was your home assignment 1. Then we justified the fact that white carbon has high DEBYE temperature and lead has low DEBYE temperature. Then we discussed the high temperature limit and low temperature limit, where I gave you 2 more home assignments to do. We said in high temperature limit, DEBYE equation 2 reduces to DeLong-Pettit law, and at low temperature, it predicts T cube dependence of Cv. So that was our lecture. So this is all for today. Go Prepare your exams. Don't waste your time. Go through all the video lectures and do not forget to like, subscribe, share my channel. You can comment in the comment box also. Thank you. God bless you. Assalamu alaikum.